All right, so welcome to Lecture 3. Today we're going to start talking about some kind of like the building blocks of these deep machine learning algorithms. And we talked about this a little bit in the last lecture when we discussed supervised learning. And again, to kind of refresh, which we'll talk a little bit about it more, right? When you're supervising learning, when you have supervised learning, you're taking data that you already have that has some kind of structure given to you by way of labels. And then you sort of try to develop a model of some kind that, given the data that you have, can then predict your data the output, the ground truth that you've seen. And so in this lecture, we're going to talk about these linear models, this way to approximate certain machine learning algorithms, well, basically trying to approximate these models of really, really complicated functions out in the world that we may or may not know anything about. And we're going to try to approximate them with these very simple linear combinations of our underlying feature data. And so let's kind of jump into it. As you'll see, almost every machine learning algorithm that we're going to talk about is going to be based on some combination or composition of these things that we're going to talk about in this lecture. So I did go into some depth in these particular subjects, although I am kind of breezing through it. So if you're keen, please let me know. Every one of these slides can basically be a lecture in of itself, practically. In some classes, in machine learning classes, we'll literally do that and talk about at length all the kind of pluses and minuses. And I'll try to do my best to sort of give you an overall picture of all these different pieces and how these like machine learning algorithms work, because these underlying concepts do power pretty much every deep learning algorithm there is that I'm aware of, except things get a little bit fancier, and I'll kind of bring that up in each slide where you might see that. So yeah, let's kind of jump into it. So if you recall from last time, supervised learning, we are given a data set which includes a bunch of data, like features, in this case, a space of X, which may be one-dimensional in the example here, or it may have many dimensions. So right, we have multiple values of X, X1, X2, X3, and so on. And for each set of X's, for that space X, for each one, we have a respective set of Y's, or a Y space, right? So for one of the examples we brought up in the last lecture was, for example, housing prices, where the features may be the size of the house, how many floors, how many bathrooms, these kinds of things, and then the respective Y value would be the price of the house. And we can kind of create a model that tries to predict a particular house cost based on these different parameters of a particular home. And so the goal of supervised learning is to sort of approximate this function g that can take these values in the space of X and transform them into the space of Y. And if you're coming from a computer graphics background, you might kind of see a lot of parallels here in terms of what computer graphics is trying to do, where we're taking, in our case, say, X, which is a combination of points in space and materials and so on, and Y is the respective pixel value at a particular point, or a texture, or what have you. So really we're just talking about transforming data in a particular kind of way. So one of the sort of simplest things that we can kind of think of is, say we define this function f of x, and by x I mean a vector, right, where f of x is equal to, or defined as, these theta values, 1 theta per x parameter, x feature, and we're saying that we're going to try to approximate f of x as g. So we don't know what g could be some really complicated function with a lot of different stuff going on. As we'll see, this works for random values of, where g is entirely random, and this actually works to some degree where we're trying to fit this approximator to a very complicated function. If you think about randomness being the most complicated thing that we can model because it's not modelable. So yeah, that's kind of the function that we're going to define. So in this particular scenario, we're going to have one parameter for each feature right? So if we have, a bunch of different things like number of bedrooms, how many floors, say we have like 10 or 10 different features of a particular home, then for each one of those features we're going to have a respective theta. I should also note, and we'll talk about this more in the next few slides, that x of 0 here is sort of defined as 1. So we would actually have 1 through 10 features, but we would also have this additional theta of 0 parameter. And we'll talk about this is actually what's called the bias parameter. And if you think about a linear model, you can kind of imagine, moving it up and down in y that is irrespective to the actual values of the underlying features. But you can kind of imagine that we could also invent new features. For example, one is a combination of polynomial features, as shown below. Right, we can define a particular x of j, which is equivalent to these different a0 plus a1 of that feature x, and plus all these things. So we can actually kind of define these new kinds of features as well. But as we'll talk about in kind of the later slides, this is something that you want to do when you kind of know something about the underlying behavior of the data. So if you know, for example, that the data is linear in sort of a relative thing, you probably don't want to do this. But if you know that the data kind of undulates a little bit and it might have these sort of curves associated with it, you may want to use more complicated features for the underlying model. But as we'll see in kind of later machine learning techniques, especially in the context of deep learning, this is actually not very often done. But for more traditional modeling, you will find the value of this, where you will really just want to model it as this linear combination of features. But in the context of features, we can have as many features as we want, given that we extrapolate from the data that we have this new set of features. For example, another thing you could do is add features together. So you have x1 and x2, that you only have two features, but then x3 is defined as x1 plus x2. As far as your algorithm is concerned, it's just going to see a bunch of features. So it kind of all distills down to the same underlying linear model of x0, x1, xn, and so on, except that you may attach more things there. So that's kind of an important note to make, but not something that we're really going to deal with very much in this particular lecture. Although if this is something of interest, I'm happy to kind of go into it in detail in Discord or in an additional lecture, so please let me know. So you can kind of take a look at this function and say, oh hey, like, it's a linear function, it's a linear set of equations, we can solve directly for this, and that is true. We can essentially say, well, our goal in terms of this model, say we have these values and we know the y's, right? Then we can basically create this definition of the mean squared error here, and the mean squared error is going to be equivalent to the sum of every y value minus the approximation of y. So if you think of f of x as a way to approximate or predict what a potential value of y would be given these thetas, then you have this equation of yi minus y, which is just kind of the distance between these 2 points. So say, again, like we predicted the house price to be $450, but the real house price was $500, so the distance there is 50, and then we take it to the power of 2, and then we sum this for every single example. So in the case here of m, we have m examples of data, and the y approximator is actually this f of x of ours. And so we subtract that, and then we kind of extrapolate this down, and you can eventually see, right, that the definition kind of vectorized of this is then this loss of parameterized by theta is equal to y minus x times theta transposed times y minus x of theta. And so this is just kind of a vectorized representation of the above, and we've dropped the 1 over m just to make this equation kind of nice. And keep in mind right here, the only thing that I've done is f of x, this right here, has been popped in there. And so you can kind of see that when f of x, when you pop it in, you get this beta term. The beta term being the bias, by the way. But again, I've dropped that again for the purpose of just sort of clarity to make this sort of look nice. In terms of the below, the loss parameterized by theta, the reason that we don't see the beta is, again, you're going to go back to this equation here, where you have theta 0 times x of 0, and we just define x of 0 to be 1. So if we say, in theory, if you look at this f of x equals beta 0, which is our bias term, xi, you can in theory say, okay, we're going to start at I equals 0, but x of 0 is equal to 1. It's going to be kind of equivalent to the same thing. So anyways, just making kind of a long-winded explanation of why this equation comes out to look a little bit cleaner than you might anticipate if you were just to pop that in directly. So we can say that this is the equation, and if that's the case, then we can kind of solve for the loss in terms of directly by so so what are we trying to do here, right? The loss is something that we're trying to optimize. We're trying to reduce the error down to a point where we have essentially a derivative of 0. Why is that important? Because we're trying to get to a place where we've gotten to a minima of some kind, and at a minima we have the derivative is equal to 0, right? Because it's flat. I'm not going to go into too much detail about why all the kind of guarantees here and how to actually do this, but you can kind of take the derivative, the multivariate derivative of the loss respective to the thetas, and kind of arrive at this negative 2x transpose times y minus x of theta. And if you then take that and you plug that into equivalent to 0, you eventually kind of get to this form of the pseudo inverse of x times y will give you the the parameters theta that will minimize this least squares loss, this mean squares error. So that's if you've seen this before, this is just the normal equation method for solving directly a large set of linear systems very, very directly, and it's very effective. But there's a lot of problems with this, and we talked a little bit about this in the last lecture. So hopefully this math doesn't kind of scare you away. It's not super important, because what happens is this particular equation, this normal equation method, has a really big issue with sizes of x and y. So for example, given m examples with n features, this resulting x matrix is going to be an m by n matrix, and for large values, this particular calculation can be quite intractable. And so, what can we do, right? So if say we have 10 million samples and with hundreds, if not thousands, of features, right? What can we do with this sort of mean squares error definition, such that we can then potentially leverage this derivative in a way that helps us sort of solve this, get to a solution that perhaps isn't right analytically the correct answer, but rather something that we can kind of get nearer. So say we know we can solve for the derivative, right? This derivative here, for example, does not require calculating the inverse of a very large intractable thing. And not to mention, we're looking at the multivariate derivative, so could we actually, instead of thinking about this from a multivariate standpoint, maybe do this per example? So for every example, we know what's the respective loss relative to that particular example. So we're going to answer this question in just a moment, and to do that, we're going to look at the sort of one-dimensional example. So right, if you look back at this function here, f of x is equal to theta 0, x 0 plus blah, 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 we're thinking about these, massive, feature-based data sets. Well, what if we just kind of talk about modeling one dimension, right? And everybody is probably very familiar with this equation, right? You've seen y equals ax plus b. That's all this is, right? This is just a linear, this is the formula for a line in x of y. But instead of a and b, we're using theta 1 and theta 0. And so we're defining our f of x now as theta 1x plus theta 0. So now we're going to generate a bunch. And by the way, this data is out of a Jupyter notebook I wrote up to generate these images, which I've included in the Notion page. So feel free to take a look at that code if you're interested. It's just garbage code just to do something and to show how this stuff works, but it might be helpful. So let's generate some random data. You can kind of see the modeling for this data is simply a linear, and plus add to that some random perturbation off of it. So we've kind of ensured that our error is going to be, some bound off of this particular line. So this is just kind of randomly generated, but we're giving it some kind of general shape. As you can kind of see, it's a sort of a linearly growing, randomly scattered, data set. And so now, let's just choose a random set of thetas per f of x equals theta 1x plus theta 0. And as you can see, this random choice is pretty bad, right? Like our theta 0 is down here somewhere, right? That's the y-intercept, right? Theta 0 just is equivalent to the y-intercept, which is around 2, which we can see here. We kind of want something closer to like 13, right? But although the slope is not so bad, the slope seems to be kind of accurate, but the error here is going to be quite high. And so, but once in a while, if you just kind of keep trying, if you keep hitting the button, once in a while you'll get a model that's actually kind of close. So this is kind of a interesting result, right? Like already, without even doing anything, we just randomly chose these two values out of the ether. We have a line that seems to kind of look a little bit like what we expect to see. So, okay, this is the beginning. This is step 1, right? So now, if we use the analytic approach, we can directly solve for this. So if you can see below here in the bottom left, the blue line is our randomly chosen values, and the green is solving directly for this parameters theta by way of the normal equation method. So we take all of the x's, and in this case, by the way, the x's haven't included 1 for that theta 0. We transpose, multiply, negative, take the inverse, multiply, blah, blah, and eventually we get to the values of theta, and our, it immediately gets us to a minimum loss that we want. However, now you can kind of see the problem. On the right here, this is an example where I've done the same thing, but with 10 million data points, right? And in this case, it takes a very long time, even for a one-dimensional function, to resolve this particular thing, because x is a 2 by, or a 10 million by 2 matrix, and so now that calculation is quite large. Now, one thing that's kind of interesting here, as you'll notice in the bottom right, the error that the error being defined, by the way, as this mean squared error, right? The error is 0.0047 versus 0.00027 for our normal equation versus. So we still have error. Like, this doesn't give you perfect, because no matter what you do, the line can't map the values exactly. It's just going to give you a relationship and reduce that mean squared error. But why is this value still going down? Because here the error is quite high, like 1.5, but here it's 0.0047, which is quite small. And so I think the thing that you kind of want to pay attention to here is this 1 over m value, right? Where a 1 over m in this case is 10 million, so 1 over m is 1 divided by 10 million. And so your error is still going to be respectively small, getting smaller as your number of data values get up, given one thing, and this is an important distinction here, a bound error. So this modeling for these values, it was basically just a linear, linear thing plus minus a range, like a uniform variable on a range. So you're guaranteed that it's never going to go outside this red region or less, and so that means that we're on average on the expected value of the error is always going to be within that bound, and then we're dividing that by 10 million. And so that's why with this particular example, even though this is actually kind of a good thing to pay attention to, right? Your error may be going down as you add things that are not necessarily better fitting, because right here that blue line clearly is not very good, but the error of that blue line is 0.0047 versus the error of this blue line on the left, which is 1.5. But if you were to say which one's a better fit, the blue line's better fit. So you do want to kind of think about that when you're comparing models sometimes. It's an important thing to kind of look at. Well, cool. So this is great, but it's clearly not something that we want to do, especially not for high-dimensional models or for things where we have a lot of data. So what else can we do? Well, let's talk about this this algorithm called gradient descent. So what we can do, and I've noticed that the I don't have the right font installed, which has distracted me. So well, okay, I'll keep going because I can talk plenty without the font being correct. So whatever. Let me stop. Let me just switch over to something else. Okay, switch to the PDF. Looks so much better. Am I right? Whoops. Okay, why is that there? Cool. So what we can do is we can use this algorithm called gradient descent. And what gradient descent does is we try to calculate the derivative of the loss respective to a particular parameter. And once we have that derivative, then we subtract that times a learning rate alpha from our parameter. So like to kind of go through this, on the left here you can see the loss as defined by x times theta j. And the reason I want this form is because I want the derivative of the loss respective to theta I, as you can kind of see here. And so when I take that derivative, what I'm going to get is, oops, sorry, there's an errata in this. It shouldn't be, this is not equal. I want to take the derivative of this. This is kind of plugged in. I'm sorry about that. But anyways, what I'm doing here is now the derivative of theta L of the loss respective to theta I is going to be equal to essentially this value here, which is one over the sum of the yi minus xij theta j times xi. So a little bit cleaner of a notation is down here, where you can see the derivative of the loss respective to theta I is equal to the correct y minus my predicted y times that particular x value, that x feature. And I do this for every theta that I have. I'm not going to go into super depth on this. I think there's a lot of really great resources on gradient descent in this definition. We'll go through this more and more in terms of other algorithms. But if you all want me to kind of go into depth about this and how to derive all these and what this actually is doing behind the scenes, let me know. I'm happy to go deeper into that. But ultimately, this update step here in the bottom right is really what you're looking at in terms of gradient descent, where for every parameter that we have in our model, we take the previous value and we subtract from it this derivative of our loss times this alpha learning rate. And keep in mind, this gradient descent algorithm, this equation for the parameter, is always true for whatever loss or for whatever objective function that we're using, whereas this derivative of the loss here on the left is specific to this mean squares error loss that we've defined in the top left here. So you may have different loss functions, and we'll see another one in this lecture, and in that case you want to derive it differently, but the update is going to be the same. All you're really doing is you're taking the derivative of that loss respective to that particular parameter in your model. And it's really just that simple. There are a lot of different kinds of models, there's a lot of different kinds of losses, but really this is the update. And what this is doing is it's taking the parameter, it's determining which direction the loss wants to go to minimize per respective to that particular parameter. So if you think about being on a hill, right, you have two directions, north and west, or north, south, southeast, right? And so for each direction that's orthogonal, you say, oh, this direction, I want, the slope is this way, that direction, the slope is that way. And that's all you're doing. Now you take a particular alpha, which is your learning rate, and we'll talk about learning rate selection and what these values should be, and then you subtract from your existing parameter that derivative to some degree. So in other words, you don't want alpha to be too big, because otherwise you start ping-ponging all over the place. If you make it too small, you're not going to make much progress very quickly, which we'll talk about plenty in this lecture. But this is sort of the underlying idea, which we'll visualize it as we kind of go through. So here's kind of an example of gradient descent applied to our random data. So on the left here you can see we've chosen some random model, and our loss is quite high at 1.26. And then after a particular number of gradient descent steps, right, we eventually get to this line that fits the data relatively well with a loss of 0.089. And you can kind of see that the line seems to really fit our data quite well. And on the right here, this particular plot is the loss plotted over the iteration. So you can see that around iteration 400 or so, we're starting to kind of flatten out the loss. So additional iterations of the algorithm are not really improving the loss particularly much. But there's a big problem here, and you can kind of maybe already see it. This particular algorithm, as you can see, goes through every single data point. So for this case, that's fine. We have 100 data points. It's not a lot for a computer to deal with. But say we have 1 million or 1 billion data points, and this equation, while it does avoid this need to do this inverse of a very, very large matrix calculation, still does require us to do, you know, 1 million or however many number of of calculations for every iteration. So is there something, can we do better? Is there something that we can do better? And so the answer to this is what's called stochastic gradient descent. And stochastic gradient descent is actually just like normal gradient descent, except instead of running over the entire data set, we're going to choose a random selection of data points inside of our data set, and we're going to run this calculation on them. So instead of doing it for every single data point that we have, we're going to say choose 10 or 20 or 100 or whatever your what's called the mini batch size is, and we're going to calculate this derivative at this loss and then respective derivative on that loss for only those number of calculations. And that the difference is kind of seen here, but the result is actually surprising in terms of how equivalent it is. Right on the left, we have this is gradient descent without this mini batch approach, and on the right we have stochastic gradient descent. Now, these two took about approximately the same amount of time, and so you can kind of see that in the same amount of time we can run way more iterations of stochastic gradient descent, because here we're doing all 100 data points every single iteration, and here we're only doing about 10. So the overall speed is going to be much, much faster. However, on the stochastic gradient descent, you can kind of see this noise that's being applied to the loss. And the reason for that noise is, given a sample set of only 10 examples, right, your gradient is going to be specific to those and may ignore the rest of your data. So it's kind of going to go over here, and then it's going to go over there, and it's going to be kind of overcorrect a lot. And over time will eventually, still bounce around, because you're dealing with these sort of randomness in the selection that's introduced for the mini batch selection as well. But it works quite well, and this is usually the approach that we take in machine learning versus doing it for the entire data set, because sometimes our data sets are really big, like, for example, ImageNet, which is one of the image classification data sets that we discussed last lecture, has 1.2 million images. And okay, if this is hard enough for a one-dimensional thing, imagine doing it for a image that's quite large. And so yeah, stochastic gradient descent tends to be the general strategy that's taken because it's much, much faster. And you can overcome this noisiness in other ways, as we'll discuss in this lecture soon. So let's kind of move this into higher dimensions, right? Up until now, we've been talking about just a one-dimensional signal. So what about two? Well, the answer is it's actually quite simple. The only thing we need to do to add more dimensions is to just add more of these values into our f of x. As we showed here, right, previously we only were doing the theta the parameter update for two parameters. One parameter was our bias, so that meant we weren't really doing too much. We were just summing this because our x of I in this case was 1, so we're just doing this. But in the case of multiple parameters, multiple features, I mean, we just have to do this more times and for each feature. So this immediately transfers into higher dimensions, although I didn't do an example because the visualization gets arbitrarily more difficult to show. So yeah, that's kind of it. Here's a visualization kind of what gradient descent is doing. It's a pretty popular visualization. So if you can take a look at this function, this loss, and which is parameterized by theta 1 and theta 0, right? In this case, the loss is going to have these minima and maxima. It's spread out. It's going to look kind of like this three-dimensional function. And say we start at a particular point, right? We're now calculating the gradient of this function in these with respect to these two dimensions. And what we're going to do is we're going to sort of like walk down the surface, the manifold of this function, in the direction of the maximal gradient. So if we're here, the gradient's going to be this way, and we're going to go in this direction wherever things are sort of steepest, where things will get better the fastest. And by better, we want a reduced value of the loss. And so we can kind of start here, and we move down, we keep going, we keep going. And you can see the gradient kind of reduces as we go down because we're flattening out. That manifold is getting kind of flatter as we go. Now, what about these areas, right? Like, you might be looking at this and being like, hey, wait a minute, like, what do we do when we get to a situation where we're in a local minima? How do we ensure that we don't fall into the wrong one? How do we deal with situations where we're really flat and maybe we're moving really slowly? Well, these are real kind of concerns for a very, very limited feature model. This is definitely a problem that you have to think about. However, most machine learning algorithms don't deal with one-dimensional data. Most of our things that we're going to be talking about live in extremely high dimensions, right? For example, an image, which a 32 by 32 by image with 3 channels of color is quite a high dimensional space because each one of those pixels is a different dimension, and each channel is another an additional dimension, kind of multiple on top of that. And so you can kind of imagine very quickly that in high dimensional space this doesn't really become an issue so much, because we're basically like guaranteed a direction to go in any particular point. And so this sort of 1D problem is not a very good representation, right? Even in the case of our housing prices, say we have a 10 feature data set for a housing price, and we have a lot of these houses that seem to be around the same number of rooms and the same number of floors and the same square footage, yet vary wildly in their price, right? Where it's like, okay, well, here's like this flat area of the loss function because they're all very similar in that kind of respect, but at the same time, right, their area codes are very different, or the school quality is very different, or whatever. There's always some dimension that we can use to kind of make progress on this sort of irregular manifold that is very difficult to visualize once we get beyond just 2 features. And actually in this case it's only 1 feature, right? Because our theta 0 is our bias term. So as soon as we get into 2 features, this manifold is no longer a 3-dimensional manifold, it's a 4-dimensional manifold, and as soon as we have to 3 features, we have a 5-dimensional manifold, and so on and so forth. And that's something to kind of think about in terms of just how these things are really, really hard to visualize. I had another slide about high-dimensional space, but it didn't seem to come through, so we'll skip that. But one of the things I wanted to kind of talk to was just high dimensions tend to start getting really weird and a little bit unintuitive. And I might include this as a link for resources for you guys to take a look at, in particular with regards to kind of what's the hypercube sphere paradox thing, where you have, well, maybe I'll talk about it some other time. So now we've got a kind of this relative algorithm that we can apply to fit linear data. That's quite good. But how do we apply this to classification, right? And so in the context of classification, we want to determine this decision boundary in a way. We want particular values that are on one side of the boundary to, we basically want to say, okay, here's a line, and on this side of the boundary is one class, on the other side of the boundary is a different class. And so we're going to talk initially about binary classification. And so to really kind of figure this out, we want a function that returns values that are close to 0 for the black value, so that's our first class, right? And we want values close to 1 for the blue values, which is going to be our second class. And if you can, there's a lot of different functions that we can kind of use to do this. You could do this with linear, but linear gets a little bit hard in terms of capping it and maximizing it. So we usually use what's called the sigmoid function, which is which is defined as 1 divided by 1 plus e to the power of negative x. And as you can kind of see here on the right, the sigmoid function for values that are above 1, that are getting close to infinity, it kind of saturates at this value of 1. And for values that are getting to kind of negative infinity, it saturates at the value of 0. So this is perfect, right? Because if we have some way to input values into this equation, we can say, okay, well, for things that are blue, we want a really, really high value. We want the theta times x, right? Theta being the parameters, to be equal to a very high value. And for these black values, we want those particular values to be closer to sort of negative. Like we want to maximize the negative of those. And so if we can kind of come up with a linear model that gives us this sort of relationship between the blue values being high and the black values being very low, meaning kind of positive and negative, we can then map that and have a function that tells us which is which, right? And that line in between is going to be generally that respective parameters that linear decision boundary that we defined, if we can figure that out. So how do we do that? So the way to do it is just we pop it into x, right? So in this case, we have our theta 0 plus theta 1 times x1 plus so and so and so forth for each parameter. Now we have to kind of rethink our loss function a little bit, because what we want to do is when the class is equal to 1, right, we want our loss to be this function here. And why do we use log? Because log, in this case of this sigmoid, right, as the log gets closer to 1, right, we're going to, one moment. Sorry, I always forget how to explain this well. So, okay, so the value of log as it gets closer to 1, so remember that f of x here is going to respectively, saturate at 1 or go to 0. And so log, as you get closer to 0, you're getting closer to infinity, and as you're getting closer to 1, you're getting closer to 0. So that's kind of a nice attribute, because when y is equal to 1, what we want is we want our function f of x, our sigmoid classifier, to be close to 1. So if that's true, if we get a value of 1, that loss is 0. And in that case, we're correct. For the class of y being equal to 1, then we have correctly classified, and that means we have a 0. But say we classify in the value of 0, and we provide them, then the loss is approaching infinity. And so we're maximizing the loss. And so this way, the reason we want to do negative is because this is the loss is going to be equivalent to we want a negative loss. We want to minimize this versus maximize it. And so similarly, when the class is equal to 0, right, all we have to do is we take 1 minus 0. So if the classifier is equal to 1, then that's incorrect, and we get a log of 0. And if the class is equivalent to 0, then we get a log of 1, which again is a 0 loss. And again, we take the negative because we want to minimize this. So to combine the two, we have this what looks like kind of a scary function, but it's quite simple, right? Where we, over all of the data sets, all of the mini batch in this case, we take the classification, the correct classification, by the way, right? This is if it's the value. This is the supervised aspect of it, right? So our data, our particular example is class 1, so y would be 1. If it's actually the true class is 1 or 0, and so then we take when we multiply that by the logarithm of our classifier against the data set, the features. So in other words, in this case, say that the classification, the ground truth classification was 1, but we incorrectly classified it, and we got a value close to 0. then the loss would be quite high because we have 1 times a very large number here. And then over here, this is just going to be equal to 0. So this allows us to kind of treat the correct or incorrect independently. And so when the correct classification is 1, we're looking at this term. When the correct classification is 0, we're looking at this term. And keep in mind, this approximator is not going to usually be equal to 0 or 1. It's going to be some value in between because we have these parameters. So these are going to be non-zero values. And the negative just means that we want to minimize this term because we want to sort of go in the direction of the low loss as we can. And so I'm not going to go into detail about how, but actually the derivative of this in respect to a particular parameter just pops out to be exactly the same as linear regression. So you can kind of see that now the derivative for a particular parameter is going to be the correct y classification minus the classification that we predicted times that particular parameter value for that mini batch example. And then you sum across the entire set of examples. So again, I'm not going to go super deep on this stuff. Again, like some classes will spend the entire class just talking about logistic and linear regression. I'm assuming you kind of know some of this stuff, or maybe you've come across it before. But keep in mind, like a lot of the stuff you don't have to build. We'll do it for our first assignment, but it's a good exercise to understand. It's not super hard to do. But don't get too bogged down in the weeds if you don't really grok this math right off the bat. But it's just kind of, in a way, it's like the code translates into, it's like the code is easier to understand than the math in many cases, because all we're doing is we're doing two different things for when the value of y is 1 or not, which in code is an if statement, right? So this works really well for a binary classification where you have two things, but what about if you have more than two things? And so then we introduce this concept of one versus all. And what you do in one versus all, say you have 3 different classes, well, then we have 3 different classifiers, and in each classifier we treat the target class, as one class, and everything else as another class. And so we just have 3 different binary classifiers, and we train them independently, and then to predict, to actually use those classifiers, we run our new value through each single one, and then we say, okay, the one with the maximum is going to be the correct class. And so this is one approach to doing multi-class classification using logistic regression, which is also, by the way, the name of this algorithm. So before we had linear regression, and logistic regression is essentially linear regression with this sigmoid, or this nonlinearity, wrapped around it. And we'll see actually that there are other nonlinearities that we can use. So this function, this approach, this one versus all approach, does have a kind of limitation, right? Because the only way that we really have these classes interact with one another is by way of this maximum. So there's no way to sort of create these interactions between the classes, right? Our decision boundaries are largely independent. You know, right now it's basically like this blue class versus these two, this gray class versus these two, but it's not like this class versus this one and this one. It's sort of independent, and then we kind of get an answer. So softmax is, and this is, by the way, very important for machine learning models, as we'll see, because this is largely the way that most models kind of do their final classification on a complex feature representation, as we talked about in the last lecture. But the softmax essentially kind of combines this concept of one versus all into a model, into a loss function that sort of that includes effects from the other ones. And so the way that we do it is, say that we have these so in this case we still have 3 different classifiers, and each one has its own respective parameter values. And what we do is we take our x's, our features, and multiply them by each respective parameter values, and we get this value, e to the power of our, predicted thing each, right? And now what we have is we take the value, and this, we kind of treat this as a probability, we divide that probability by the sum of the other probabilities, and what that's going to give us is sort of the likelihood, the sort of proportionality of that particular class against all of the others. And the reason that this is important is because now we have sort of coupled the behavior of the other, the other classifiers into the output of this particular classifier. And so I'm not going to go deep into this because the process of deriving the loss, the derivative of the loss per softmax is a little bit more involved. But the derivative now of this particular loss with respect to a particular parameter takes into consideration the behavior of the other classifiers as well. So that's a very nice thing to have, because now we have a little bit of competition between the different classes, meaning this bottom value should always kind of equal to it. We'll always have some, it's always a proportionality, and so you're kind of like edging something out. When one thing goes up, the other thing goes down, and that's a good thing to have when you're trying to kind of classify across many different classifications. And so you'll often see the softmax loss being used in, say, image classifiers and things like that, versus simple binary classification, which you won't see very often. So I'm not going to go too deep into support vector machines, but this is another approach to classification, and in this case we're really using this analogy, or not analogy, but we're really thinking about this line, this linear separation, this decision boundary, and what we're trying to do is we're maximizing the distance from a particular value from that decision boundary. And so the loss is defined as this thing called the hinge loss, and I've noticed an errata here too. It should be the maximum between 0 or 1, and the reason that is because when this particular value, when we've classified 1, then this particular value is 1. Otherwise, it's going to be 0, right? So we're only classifying the loss when we have when we've classified this correctly. I'm kind of slaughtering the explanation of the support vector machine, but really the intuition here is that if we've correctly classified the value, then we're going to have a loss of 0. And if we've not correctly classified it, we have a loss of 1, or actually not 1, but the distance from that particular decision boundary. And so the hinge loss represents that, and I think there's an errata here which I'll update in the notes as well. But actually, this is very kind of easy to do, because that particular derivative is very easy, right? When you've correctly classified, the derivative is 0, you don't do anything. But when you've incorrectly classified it, the derivative is equivalent essentially to the value, to that particular value of x, respective to that incorrect that incorrect value. And so pretty easy to implement, very computationally efficient, and you'll find support vector machines have been very popular, and especially when it comes to these sort of linear classification models. So so let's move on into kind of discussion about, in this case, for example, right, you may look at this and say, well, in this case, right, in the softmax loss, you're like, okay, well, what's the derivative of that, and how do I calculate it? Well, sometimes we have these algorithms that have objective functions that are quite complicated. We don't really know what they are, and so sometimes it's really valuable to be able to debug the gradients of these functions without knowing what they are analytically. Because, say we're developing our analytical solution for the gradient, and we want to make sure that what we have is correct, or sometimes the function is intractable or has some certain parameter or certain attributes that make it non-differentiable, which we're not going to cover in this lecture, but generally speaking, does occur once in a while. And so, it'd be nice to find a way to determine what the gradient of our function is without having to directly analytically, derive it. And one way to do this is just by numerical approximation. And what we do is we take, for a particular parameter, we add to it a value of epsilon of some kind, and we then calculate the function given that particular parameter has been permuted by that particular amount. And we do this for each one of these parameters. So for theta 1, we add it, and then we leave all the rest the same, and so on and so forth. And so for each one of these parameters, we can determine the analytical gradient, the approximate gradient with respect to that particular parameter by way of adding this epsilon and subtracting, then taking the two values and subtracting them from each other and dividing by that distance. And the kind of equivalent here is you're sampling the value of the function at a particular point, at another point, it's kind of like calculating the slope and then dividing by that to get the sort of rise over run. So it's a very kind of old school way to think about it, but it works really well, and this is a great way to say if you're implementing a particular derivative, you can do this calculation side by side while you're developing your implementation to ensure that the implementation that you have is correct. And so I wouldn't, and one thing to note here, this is not something you want to do like instead of analytical gradient calculations. Often you don't even do any of this stuff, right? You just use a framework or what have you that gives you all of the gradients built in. But this is an approach to doing this such that you can kind of compare or understand what's going on underneath the covers, and it's very, very useful to kind of think about. There are other heuristic approaches. I'm not going to go super deep on this, but this is just kind of a mentioning. One approach is this idea of Nelder-Mead, which is essentially a simplex search algorithm. And so you can imagine you have this really, really complicated function. The reason this is better than here is that you don't need to do this per parameter. You can just choose these 3 arbitrary points in your space and then calculate them and then triangulate, literally, the gradient from them, and then kind of keep going and keep going. And there's an algorithm, Nelder-Mead algorithm, that sort of tells you what to do, whether it's to choose the next point or to shrink or to keep going, and over time you will eventually reach an optimum. Now, we've already talked about a couple of hyperparameters that really fit this need for search across a complicated function that may not be differentiable. For example, we talked about the learning rate. So the way that you set your learning rate really affects how quickly your algorithms will converge or not. There are other things like your mini batch size. So do I do 10 samples in my mini batch, or 100 or 50? All right. And so all of these could be kind of codified into these these parameters, these what's called hyperparameters. And these hyperparameters then can be searched by way of something like Nelder-Mead, which basically chooses randomly these values and then tries to kind of figure out where to go on those particular values. So you might not do this for the parameters of your function, of your approximator. That you would do gradient descent or stochastic gradient descent. However, with things like hyperparameters where the relationship between the loss function and all that isn't quite clear, you may want to use something like this instead to kind of speed up the search for the optimal hyperparameters. Another approach to this, by the way, is this algorithm called BFGS, or low memory BFGS. Again, there's an errata in the slides. And this is actually a second order approach to approximating the minima in a function. But I'm not going to go too deep into this, and even my understanding is relatively weak here, although it's available as an optimization technique in many different frameworks. But really what you're doing is you're calculating the Hessian, which is sort of like the matrix of second order derivatives of a particular function, parameterized by a particular matrix of parameters, and then you're applying the inverse of that to your gradient, and you can kind of speed up. But the problem with this is it's quite expensive, right? Inverting the Hessian is a very expensive thing to do. Not always directly, tractable. So, it's something to kind of consider. And there, again, I'm no expert on these kind of more complicated, what's called the quasi-Newtonian approximation methods. So, it's kind of worth talking a little bit about overfitting and regularization. We've kind of skimmed over this, and again, a lot of the classes will, that are just machine learning classes, will go really deep into this stuff. But it's important to kind of have an understanding of what overfitting is and why we have to use this concept of regularization. So when you think about the model that we had was very simple. It had a bunch of random data across this line that was just perturbing this line in a random way. And so if you can imagine instead these values which are, say, following clearly this curve, right? If you just use a linear classifier, just like you only have one line, You don't add these sort of higher level, higher order, polynomial features, you may find that this is underfitting your model. So no matter what you do, right, your error is not going to improve or really fit your model. Now, if you have too much, if you kind of you add every possible polynomial feature you can think of, and you go to the limit, all of a sudden you can have a model that significantly overfits your data as well, right? In this case, while every single value is on this sort of squiggly line, you can imagine that if we were to sort of sample this point here, right, it would not fit the data particularly well because we would get a value in a funky place and there would be a large error. This is what's called overfitting, where we kind of are too sensitive to our training data set. So the ideal is to have a way to sort of smooth out our model. So we want to have this sort of sensitivity and flexibility of many, many features and so on, but we also want to have this sort of smoother fit. And the way we can accomplish this is by way of what's called regularization. And so what I've shown below here is just this basic L2 regularizer. The L2 regularizer just uses the L2 norm of our actual parameters. And what we're doing here is we're taking every parameter and we're multiplying it by itself. We're basically taking the square of the parameters and multiplying it by this, again, a new hyperparameter called lambda. And that lambda regularization usually is like half or whatever. You can choose whatever you want, but generally speaking, a common value is 1/2. And what this is doing is whenever the values of theta, right, and the sum of them, like the L2 norm starts to go too high, then the loss goes up too. So what this is going to do is it's going to encourage, right, because this ends up in your gradient as well, right? When you take the gradient of this per the parameter of with respect to a particular parameter, you're adding lambda 2 times lambda times the parameter. You're adding that to your gradient as well. So you're penalizing the gradient for getting too big, essentially. And so what this is trying to do is really navigating and negotiating between a good fit to the data without having these very, very wacky things all over the place, without having very, very large perturbation, very large parameters. So the L2 regularizer as shown here is, one regularizer, or many regularizers out there that you'll see especially when we talk about unsupervised learning. You start to talk about, regularizing against the underlying structure of the data, such as the divergence between two probability distributions. But the L2 regularizer is quite effective. And so one of the things that kind of intuitions here is the regularizer, and this is, something that I encourage you all to really dig into because this is a very cool thing. What the regularizer represents is our knowledge of the problem. So if we know a lot about the underlying domain, right, we can in turn create a regularizer that sort of represents a prior of some kind that is then applied to our loss. So if we know that the parameters should be in a particular way, meaning they're not too bumpy, right, we can apply some kind of rule to the objective function that tries to encourage those parameters to fit a particular kind of distribution. And in this case, this distribution that we're fitting, in the case of the L2 regularizer, is we're trying to effectively kind of create a thing that sort of in linear and Euclidean space is smooth, where if I move a value and if I change a particular feature, the representative change in the loss is going to be also linear. And that's a really cool result. There are downsides to this, but what you're really doing is you're smoothing out your model. You're smoothing out the way that your model reacts to data in a particular way, which is a really very powerful concept. And I think the concept itself is more important than understanding like all these different kind of regularizers, because again, it really comes down to this prior knowledge that you have of your problem. If you know that data shouldn't fluctuate wildly, you add this L2 norm, which ensures that it doesn't. if you know that your parameters should fit a particular probability distribution, right, then you can add this regularizer that encourages that probability distribution, which is, by the way that that GANs work, right? Generative adversarial networks, the regularizer that kind of pops out of them is this concept of the Shannon-Jensen divergence, which tries to ensure that the distribution that you're producing doesn't diverge too much with the distribution that you're targeting. Although it doesn't actually use a regularizer to do that. It does a different thing, which we'll talk about kind of, in the middle of the course. Cool. So this is the part where I kind of go off and tell you a little bit about different kinds of things that you can do with stochastic gradient descent that improve your algorithm. Now, you might already kind of think, you've seen this thing, and if you're familiar with stochastic gradient descent, you might already know about some of these techniques. But this is a way to essentially have your algorithm kind of converge faster. And why do we care about converging faster? Well, we do because it's a lot of computation. A lot of these algorithms take up a long time, right? And as you've seen, it took 400 or 500 iterations for that one-dimensional model to fit random, like 100 data points of random data. If you've got things with much, much higher dimensionality, you can kind of really quickly understand, well, okay, we're talking about a lot of computation here. And so anything that we can do to improve and speed things up is a good thing. So one idea is quite a eloquent one, which is momentum. So in terms of the update to our parameter, you can kind of think about that as this vector, right? As we saw in that image of the manifold, you have your loss, and you're kind of trying to navigate that complex function to get to a minimal, to a place that's best. But if you can kind of treat that gradient as a kind of velocity, right? Imagine that velocity builds up momentum. So when I'm walking down the hill, I keep going a little bit, even if I'm supposed to go in the other way. So I kind of hold on to a bit of the momentum. And so this concept of momentum is literally that. And instead of directly applying the gradient, what we do is we maintain a exponentially weighted sum that utilizes the new gradient update as well as the previous gradient update, and we kind of represent this ratio with this value rho. So again, here's another hyperparameter, which is between 0 and 1. And in the case that rho is 1, then we're only using the new update. We're just using it 100%, and we're throwing away the previous. So that's a no momentum. But if rho is less than 1, then we're using the new update to some degree, to whatever value, and then we're also utilizing the previous update. So if that means I'm going this way, and then I have to change, I'm going to add a little bit of this here. So I'm kind of, the resulting vector is going to be this way. And if you do this, you find that you navigate that manifold much faster, because you're going to kind of overcome these bumps. It's almost like I'm going down a hill, and there's a bunch of bumps here. So instead of changing direction and slowing down and going in a funky way, I kind of pummel through those bumps, and I get to the result, because overall I'm still going downhill, even though in this particular location there's a little bit of a bump there. Often what is actually done is this variant on momentum called Nesterov momentum. And the reason for this is, like I just mentioned, sometimes the momentum, you're going to be in this particular location, and the momentum is going to the momentum is going to kind of point in the wrong direction because of the combination, the linear combination of your momentum and your previous vector and your new one. And so Nesterov does a little bit of a better job by applying the previous momentum to your gradient, then taking the loss, deriving, calculating the derivative on that, and then creating this update. And so the result is this sort of before and after versus, after only, and this sort of minor, adjustment can result in better behavior. But it's a minor one, I would argue. It just sort of ensures that the resulting update is sort of pointing in the right direction, or sort of always. Even if the combination of the previous momentum and the current gradient update may disagree or be changed a little bit. So it's a good, what it's doing is it's applying momentum to the thing before and then adding it, or subtracting it. So good to know about, because a lot of these things have these options, or you can implement it yourself. It's a good thing to know about. There's another very good kind of technique called RMS prop. And RMS prop was actually, funny enough, introduced by Geoffrey Hinton, which I've misspelled his name. A lot of great errors in this PowerPoint I've made. Anyways, RMS prop was introduced by Geoffrey Hinton as a random suggestion, actually, in a Coursera class. And so it's funny because all of the papers that refer to this particular technique just refer to, you know, slide whatever in lecture 6 of Coursera class, what have you. But what it's trying to do is it's actually trying to update adaptively the learning rate. And this does that by way of leveraging this runtime RMS, or root mean square, of the gradient. And so you can kind of see here it's similar to this velocity. Again, we're seeing this weighted exponentially weighted sum, but we're updating it based on the value of the gradient of the root mean square. And so instead of, though, applying this to the update directly, we're dividing the learning rate by this. And so what we're trying to do is we're going to say, okay, well, our learning rate should kind of go faster in areas that have small changes and slower in areas that have bigger changes. And so it's a very effective way to kind of scale up or down the learning rate. I should also add the learning rate is, you can also utilize this technique called learning rate decay, which I haven't added in this lectures, in the slides, but the learning rate decay, all it does is it just reduces your learning rate every single iteration, just by a little bit. So you like multiply it by 99%. So over time, your learning rate kind of gets smaller and smaller and smaller, because as you've seen, the loss starts to sort of taper off. So at a certain point, you're trying to just sort of fine tune your values versus in the beginning, you're trying to do this. So RMS prop does that, you know, automatically for you, where when you have areas of large, you know, change, it lets you go and kind of apply a larger learning rate, or reduces your learning rate to kind of match that, and vice versa. So yeah, it's a very similar idea to momentum, but applied to the learning rate instead. Finally, there's kind of one of the more common or popular optimizer rules today, which is called ATOM. And ATOM just kind of combines RMS prop and momentum together. So you can kind of see in the top, we calculate this momentum term, and in the bottom, we calculate this RMS prop, and then we combine them together in this parameter update. In this case, you can see this is just normal momentum, not Nesterov momentum. So you can also apply Nesterov momentum here instead. Also, you can add in, you know, learning rate decay. So what you would do is you would add this decay term here. So you can see there's a lot of these like hyper parameters, and it kind of goes back to this idea here, where you might want to have a heuristic approach to search through all these different parameters in a way that maybe is automatic. But oftentimes what happens is people just sort of mess around and try different things, and then, or kind of create a range of them and run the algorithm on small amounts of data to figure out what's the best combination, and so on and so forth. You don't have to really know too much about this stuff. Like, you can build it and add these things as you go, but it's good to kind of know what's out there. And there are other things too, like Adigrad, well, that's all I'm really familiar with, but there's always sort of new techniques that you can use in combinations therein to sort of speed things up, especially if you know a lot about the sort of loss landscape that you're expecting. So now there's another thing that we should talk about, which is how do you really evaluate how well your model's doing? And so what often we do is we have a large data set, we call it the full data set, the original set, and we split it up into at least two sections. We have the training set and the test set. And actually, with the training set, we split that up further into two different sections, which is the training set and the validation set. And so our training data, this is actually what we train our model on. And so we would extract our mini batch, right, calculate our updates per stochastic gradient descent, apply it to the parameters, rinse and repeat until our loss minimizes and we kind of feel good about what we have. Then a validation data is data that we then use to validate the accuracy of our model. So our model has not been trained on this validation set. We can say, okay, here's our validation set. here's the accuracy. Our model is doing pretty well, or it's not doing very well. And the reason that we want to split that validation set up from the test set is because the validation set's going to give us intuition about what hyperparameters to change. How do we retrain this? Do we train this in a different way? Do we make changes to our model? Do we add features? Do we remove features? So on and so forth. And so after we've done this a bunch of times, eventually we get to a model that we're happy with, and then we can then evaluate the entire model on the test set. So the test set is really what tells us how well we've done, because the test set is data that the model has not been trained on and not validated on either, right? And so often what you'll see is models that have, very good training loss, and the validation loss is pretty good too, and then the test loss is, worse than that. So we can very much overfit our training data. We can even kind of overfit our validation data, but then we take it out to the world, right? The test data that we have is very, very different than what we've seen in validation or training, and all of a sudden our model doesn't do well. So this is kind of the justification for having these three different kind of segmentations of data. And I should add, there's another thing here which we haven't talked about so much, right? Because we have this original data set that is given to us, and we split it up into the training and test, and then within training we have validation and training. That's all great and all, but the real world throws data at us that we never expect and is not going to be part of our data set. And so we have to be really kind of careful in ensuring that the data set that we have really represents the data that we would then see in the world. So you can do this in two ways. Either you try to boil the ocean and ensure a data set that is that wide and large and encompassing, or you define your problem very, very, very explicitly, right? And you say, okay, our data only represents this kind of problem. And if you look around at machine learning, this is still very much a limitation of a lot of these machine learning algorithms, which are great, but really apply only to a very, very narrow problem, either by way of a narrow task or by way of a narrow set of parameters and requirements that allow the algorithm to actually work correctly. So that's it for today. I know there's a bit of hand-waving done there, especially around SVMs, and I'm happy to kind of go into depth on any one of these models further. But next time we'll talk a little bit about epoch, or how you would implement these algorithms. And also expect assignment 1 to kind of come out, where we'll really kind of talk about these algorithms plus potentially a unsupervised algorithm as well, which I'll discuss in the next lecture or two. And so yeah, next we're going to start getting into how do you use these sort of building blocks to create deep learning models, and how you would actually build this stuff, either using the epoch framework, which again I really hope you all use, because I'll be building it up to support a lot of these ideas, or with like Jupyter Notebooks or what have you as well. So yeah, thanks again, and see you next time.